All right, in this module, we're going to start looking at the thermodynamics of point defects now that we've described them with Kroger-Vink notation. And so we'll start by thinking about a vacancy, because that's kind of the easiest thing that we can envision. And we do it by thinking first about a perfect crystal. So if I just sketch something real quick, right, we can envision everything in its correct spots, and nothing out of place, nothing in an interstitial. So this is our perfect crystal. And when we think about a vacancy, we think about it as taking or removing an atom from its regular spot and moving it to the surface. And so in that case, we would have something like this, where this is now our vacancy here, right? So our vacancy. So we've basically physically removed that atom and moved it to the surface. So this is a vacancy. So we want to look at the thermodynamics. So in all of these, we'll be looking at, we'll start with a single vacancy. And so when I write those thermodynamic quantities, I'll actually use the lowercase just to kind of clarify that we're talking about a single defect. So the enthalpy change, I'm going to call delta H. And so this would be endothermic because we have to break bonds, right? We have to break bonds to remove that atom. So again, this brings us to the point of it's endothermic. It requires energy to break these bonds. So why does it occur? And again, we go back to it doesn't minimize enthalpy, it minimizes free energy because we have to consider entropy, right? And so with that, if a defective crystal is thermodynamically stable, then the the G for the perfect crystal would be higher than the Gibbs free energy for the defective crystal. And therefore, delta G, or G def minus G perf would be less than 0. Right? So that's the condition that we're expecting if the defective crystal is thermodynamically favorable. So let's start by looking at the perfect, though. So for the perfect crystal, this G perf that I have is going to be the enthalpy of that perfect crystal minus T delta S of the perfect crystal. So just basically our definition of Gibbs free energy. So then we've talked about all the different forms of entropy. So our entropy here is actually going to be both the configurational, right, the different configurations that we have, plus a thermal. And we'll kind of limit it to those two terms. All right, so that brings us to a quiz question that I have for you in this section, which is if we are talking about the perfect entropy, that's going to be the configurational plus the thermal as I wrote on the previous slide. So for a perfect crystal, what is the configurational entropy? So what is the configurational entropy of a perfect crystal? So answer that in the quiz and then come back and we will discuss. All right, so that brings us back to the question here. So what is the configurational entropy of a perfect crystal? And that would be 0. We still have the thermal energy though. So let's go over what this is. So we're talking about the configurational entropy. And since in a perfect crystal, there is only one way to configure these indistinguishable atoms or ions, right? So we're counting all of the atoms or ions as the same, so it doesn't matter if they switch spots in an equal number of lattice sites. So that means that in this perfect crystal, there's no vacancies, there's no defects, and so there's really only one configuration, right? Everything in its correct spot. And so that omega term from the Boltzmann's equation is equal to 1, and therefore the entropy becomes 0. All right, so then we're just left with the thermal term and the entropy. All right, so let's jump to the defective crystal now. So for our defective crystal, we assume that there's an enthalpy cost to create one vacancy, enthalpy cost, right? So that means it's endothermic. And we give that term HD. So again, I'm going to use the lowercase because we're talking about 1. So the enthalpy to form one of these vacancies or defects, so lowercase d. And so if we talk about multiple then, if we want to create a number of vacancies in V, then the enthalpy would increase by the number, right? So the number of vacancies times the enthalpy to create each one. And so the enthalpy of the defective crystal would be equal to the enthalpy of the perfect crystal plus NV times HD. All right, so that's the enthalpy. Let's look at the entropy now. So for the entropy, the configurational entropy is no longer 0. So instead, our configurational entropy is going to be, sorry about the focus here. So the configurational entropy here is then going to be that mixing term that we saw when we talked about Boltzmann's equation. And so we have minus k, the Boltzmann's constant, times capital N times natural log of n over n plus nv, plus nv times natural log nv over n plus nv. So again, that was the mixing between the number of vacancies and the total number of sites, n, capital N. And this was the Stirling's approximation of our factorial solution. So that's what we have here. But also, we have to consider thermal entropy as well. Because if we kind of go back to, and I want to go back to a previous drawing I had. So if we're looking at the thermal entropy, when we talk about thermal entropy, we're talking about how these things vibrate, right? So these atoms vibrate around in the lattice, but they're constrained by the atoms around it, right? Well, if we consider an atom here then, this is actually going to vibrate differently over here where there's vacancy. So the vacancy causes the atoms around it to vibrate in a different manner. So that's what we have to consider for the thermal entropy. So let's go ahead now and look at the kind of the total effect of this now. All right, so by considering the enthalpy, the configurational, and the thermal entropies of both the perfect and the defective crystal, we can now look at that delta G. And that delta G then is going to be the process of adding NV number of vacancies. Right? So we kind of want to know what adding vacancies does to a crystal. And so delta G in this case, just to clarify, is the defective minus the perfect. And so what we're going to do is we're going to plot it. We're going to plot it and look at what this would look like. So we're going to look at delta G with the positive and the negative axis as a function of the number of vacancies. And what we see is if we plot the various, and this is just at a temperature T1, if we plot the enthalpy, this raises linearly, and the slope is the enthalpy term. Then we have, and that raises the free energy, right? Then we have the entropy term, which is the KT and then n natural log n over n plus n, right, plus n natural log n over n plus n, right? So basically the two terms here, right? So this is the entropy. So if we combined these to graph the delta G, then we get something like this, right? And this is kind of the classic curve where we initially decrease the free energy, and then it reaches a minimum, say right here, and this would be the equilibrium number, because afterwards, if we try to add any more defects, it actually raises back up the free energy, right? So we've basically adding some number of defects is favorable until you get to a certain point, and then it raises it back up. So this is known as the equilibrium number right here. And this is the delta G curve. So that's that's one part of it. Now let's look at a different temperature. Let's plot the same thing in the same way, but now let's plot T2 and look at the difference in temperature. So in this case, T2 is higher. So T2 is higher than T1. And so in this case, the enthalpy doesn't change. So that's the same term. However, the entropy term does decrease. Sorry, it decreases in overall, gets more negative because of the T term here. And so it gets more and more negative, and you get something like this, right? So that's the same curve as what you see over here. And so what happens is that you get kind of a lowering of this, and basically this equilibrium point increases. So this goes, this equilibrium number increases as this position here shifts to the right. So what this is saying is that the enthalpy basically plots linearly and increases with the number of vacancies, but the entropy term generally decreases with increasing numbers of vacancies up to that point. And when we put that all together, it gives us that minimum that we saw. However, increasing the temperature now increases the equilibrium number. And that's what we expect from these relationships, right? If we increase the temperature, we increase the number of vacancies. That's the relationship that we previously saw. And so the way we're going to, from basically mathematically, what this point is that we're solving for is the change in Gibbs free energy with the change in number of vacancies, and where that's 0, right? That's the minimum that we see here. And so we can actually write that out as well for the equilibrium number. So the equilibrium number, when this is solved for, it's actually the ratio, so equilibrium number over the total, which, since the equilibrium number of vacancies is typically small, we can approximate this as the equilibrium number of vacancies over the total, the number of lattice sites. And this is then approximately equal to the exponential of the entropy, or sorry, the enthalpy term minus T delta S vibration over KT. And this is basically the free energy term. So it's basically the same as saying the exponential of minus delta G for the defects over KT. Sorry, I ran out of space there, but basically, since this is more or less Gibbs free energy, we can approximate that as here. So, so really what we see is that the equilibrium number doesn't depend on the configurational entropy, just the free energy associated with forming that single vacancy. And it's, again, the number, the equilibrium number that we get is exponentially dependent on temperature, as we see here, and we see in the exponential form here. So again, this is one thing that we have to keep in mind. And when we're talking, so this is just for vacancies, right? However, keep in mind that in our discussions for ceramics, these are often paired defects. And so when they become paired defects, the calculations here become more difficult to do, because we have to pair a vacancy with another vacancy, or a vacancy with an interstitial. And so those equations and calculations can be more difficult.